Let's take a look at an example. So we have two vectors, v1 and v2. We are told that the set of those vectors of v1 and v2 is an orthogonal basis of R2. And it's really easy to check they're orthogonal, right? We just have the two vectors here. If you take the dot product of these two vectors, you get 0. So the two vectors are orthogonal. We want to express vector x as a linear combination of the vectors of set B. So of a linear combination of vectors v1 and v2. All right. So we want to find coefficients c1 and c2 to make this linear combination work. Now, we've learned how to solve linear combination equations before, and we could do it the same way we have done, but we do have an extra piece of information here. We know that these vectors form an orthogonal basis of R2. And we just saw that if our set of vectors form an orthogonal basis for our vector space, then those coefficients are going to be equal to the dot product of the vector that we have the linear combination of, that the linear combination is equal to, dotted with each vector in the linear combination, divided by the norm of the linear combination vector squared. Okay, that's my C1. Similarly, C2 is going to be x dot v2 over norm of v2 squared. And then I'll multiply that by vector v2. So this bit right here, that's my C2. Okay? And so we can do this in a very straightforward manner, just using a little bit of a couple dot products. We can evaluate and express x as a linear combination of vectors v1 and v2. Okay? So let's start with x dot v1. So here's v1, here's x. If I take the dot product, I get -1 times -1, which is 1. And 3 times -1, which is -3. And in the denominator, I want the norm of v1 squared. So the norm of this is going to be -1 squared plus 3 squared. So that's going to be 1 plus 9, that's 10. So square root of 10 squared. So just 10. Okay. Now let's do x dot v2. So here's v2, here's x. If I take the dot product, -1 times 3 is -3. -1 times 1 is -1 over norm of v2 squared. So the norm of v2 squared, so the norm of v2 is square root of 3 squared plus 1 squared. So that's square root of 10 again. And then when I square it, the square root goes away. I'll just get 10. So 1 minus 3 is -2. -3 minus 1 is -4. And so I get -1/5 v1 if I simplify the fractions, minus 2/5 v2. We were able to do that without the use of any calculators real quickly, just because these vectors are orthogonal vectors. Okay? The basis vectors were orthogonal vectors. If this formed a basis, but the basis was not orthogonal, we would not be able to use this trick.